of training or lecture on bilateral symmetry. All right, we have been looking at this for some times now, and I want to add to that which we have already presented to us before, tutorially. And because this particular session is very important, is because the subject itself is very technical. I mean, very technical. If you don't understand it, the background concept properly, especially the mirroring part of the concept, you will not be able to analyze and present the result appropriately. Okay, so when you look at the screen, you'll see what you're seeing now. You can look at this this particular one. Is we are looking at object symmetry, for example. Now it's more common than matching symmetry. Okay, so here we see this particular line is called midline or medial axis or mythical line. All right, so this line divides this particular object or this organism into two equal parts. Meanwhile, there are two sides here. I mean, one side here, one side here. So these are called pair. These two sides are called pair landmarks or pair sides. All right. So this, whatever you have on this side, you must have on this side. What that means is this side must align with this side. All right. So look at the example here now. Look at it. This one you have you have this here, you have this here. Okay. You have this here, 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 you have this here. So these are called paired. They are paired now. So the same thing happened here. So the pair now is 4, 3. So 4 pairs 3, 6 pairs 5, 8 pairs 7. You see that? Okay, if you come here now, you see 8 pairs 12, 9 pairs 11, 7 pairs 13, 6 pairs 14, 5 pairs 15, 4 pairs 16, 3 pairs 17, 2 pairs 18. So you must understand these pairs now because it's very important. Without understanding, you cannot compute anything on it. All right, so that's why I have to explain this critically, because when you go further, you understand that they are the majorly most important part of what you really need. Okay, so if this line you are seeing, this you can see this one having 3 lines. All right, the thicker one is called original configuration. This is the thicker one here. Right, this particular tiny one is called a mirror configuration of the original one. This is mirror, and this is called label. The third one is called label. So we have original, we have mirror, we have labeled. Okay, this happened when you have finally finished your work. Though they happen behind the scene. Actually, you are not seeing them physically. They are happening behind the scene as you are computing it. They are happening behind the scene. But I'm just trying to explain the concept behind it. That's why I'm showing you these diagrams. All right. So they are happening behind the scene. So here the same thing happened here. You can see this now. You have the blue, the black, and the red. Okay. So here we have the blue one is original. Okay, configuration. We have the mirror one, and we have the labeled one. So, and in the middle, of this one, you have a 1 and 2. This 1 and 2 is called unlabeled. It's called rather unpaired landmark. Unpaired. This unpaired. See, we have only 2 unpairs. 1, 2. All right. Here too, you only have 2 unpaired. 1, 2. This is number 1 and number 10. Yes, number 1 and number 2. That is 2 landmarks unpaired. All right. So the same thing happened to every other thing you'll be doing under symmetry. You have paired and unpaired landmarks. So the number of pair, the number of pair you have here must be equal to the number of pair you have here. Okay, so if you have 10 pairs here, you must have 10 pairs here, and they must be homologous. All right. So if you have 20 pairs here, you must have 20 pairs here. All right. But here in between here can be any number. All right. So here we only have 2. Sometimes you have more than that. You can have 10. You can have more than that. So depend on your object or your specimen you are dealing with. All right. So this is just a sample of object symmetry. So if you go further, you understand that look at this here, this sample face with black marks here. This sample face here, look at it. You have landmark here. You have here. So if you look at this now, you see this one pairs with this. This one pairs with this. All right. So that is how all each of them, this one pairs with this one pairs with this. So you must understand how they pair. Look at this, or look at this also. This one also pairs with this one pairs with this, 16 also pairs with this, all right, 13 pairs with 12. Okay, so the one in the middle here are called unpaired landmarks, unpaired. So if you look at the same image now, I converted to original and mirror image. Now this is original mirror, not labeled now. So because when you are dealing with it, just after you have finalized it, then the labeled will now come out. Okay, but when you are still drawing it, you have original and mirrored during configuration, during processing. But when you finalize getting the result, you now have what labeled copy is the effect now. So now we are looking at it, and this is original configuration, this is mirrored now. So here you can see that this is what you have what you have here, but in different form. So you have this one pair this one now, this pair this one pairs this, understand? This 13 pairs 12, the same thing we have here. The same thing we have here, 16 pair 14. Okay, so this is how you configure your landmark, I mean your drawing, so that you can be able to know, because you're going to group them separately. Those pairs one you need to group them, and those unpaired one you need to group them separately. So we see how it is done. The red line here, the red points here are the unpaired landmarks. 5 is unpaired, 6, 19, 15, 18, 17, 20. They are unpaired landmarks. So they are in the middle. They are called midline or midpoint or media axis. All right. So these are the concept behind it. So you must understand this before you proceed further. Now look at it for matching symmetry. Now I showed us last time this hand. This is a separate hand now. Okay, left and right hand. All right. So this left and right hand now you can digitize them separately, but you must have the same homologous positions. Okay. If you decide here, you put here too. Wherever you put here, you put here too. So that is how you digitize them. So they are separate components now. So you can see them. So it's the same thing with wings. This is insert wings. You can see here. So they are one side here, one side here. So digitize them. Wherever you put on here, you put on here too. The same positions. So that is the concept now. So for example, look at this wings here. This is fly. You can see this left and right wing. You can see here. So when you digitize here, the same thing you place on this one. Look at the landmarks here. Okay, landmarks here. So this landmarks here now you have the same thing for this second one. All right. So you can see you have 13 landmarks on the 13 landmarks for this fly wings, or sometimes mosquito wings. You have the same landmarks here. Look at this 13 landmarks. All right. So you have the same thing for the other side. So you now run your analysis and see what you get. All right. So I think in matching symmetry it is easier because you deal with individual side separately, even though you have the same landmark upon them, on them, but you are not dividing pair and unpair like the one of object symmetry. All right. So that's the difference. So look at this. What we are dealing with now. This is our experiment, our specimen now, sample. Look at this. This is one of the sample I showed the other time that we digitized, if you remember, 22 landmarks. So you can see, if you look at it critically, you understand that we have 3 with PS7, all right. So 4 with PS8 here, 20 with PS22, all right. 12 with PS13, all right. 19 with PS21. 16 with pair 17, okay, and in between you now have what? 9, you have 10, you have 11, you have 14, you have 16, you have 18. So this is called midline, all right, and the rest are called paired landmarks, all right. So look at it here. This structure here now. You can see this midline now from 9 to 10 to 11 to 14 to 15 to 18 are called midline. Okay, or otherwise known as unpaired landmarks. How many do we have there? 1, 2, 3, 4, 5, 6. That means we have 6 unpaired landmarks here. All right. Now, how many do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 paired landmarks. So if you have 8 here, you must have 8 here. All right. So this which means the same thing we saw here now. This 3 pairs 7. Okay. 1 pairs 6. 2 PS5, 4 PS8, 20 PS22, okay, 12 PS13, all right, 16 PS17, 19 PS21. So this is the concept actually, but sometimes you may not, if you don't know how to do this, you want to, especially if your landmarks are many, you can run into a problem. But I will show us a very simple where I got this from. This one I got it from Morphometrics. I will show us how to do this in case you have many landmarks. It is easy to do when your landmarks are not many. You can still draw them out, but when you have many landmarks, you can be confused sometimes. But when you have a complex object, complex specimen, all right. So I will show us how to do this in Morphometrics to give you this particular component out. All right, you'll be able to know if your landmarks are not properly positioned to give you a symmetry concept. It will give you error. It will not show. You will know that oh, this is not correct. This is not properly placed. It is properly placed. It will generate this out for you automatically. See this one in the middle like this in color, in this green color, and this one in the side like this. You see automatically. So you can bring out this image and compare it, use it to follow it as a pattern for your experiment to compute your data. So let's proceed further. This is a result concept now. So look at this now. Look at this result. This is what you get later. So the way people interpret result is not the same actually. Depend on your hypothesis or the problem at hand we're trying to resolve. Okay. Now look at this now. This is just a sample result that you will get. This sort you will get everywhere, but the way it is arranged is not the same all the time. Okay, so the individual arrange this or present this particular tag or this particular table depends on based on their what they are working on. All right, this first line is here. This individual is called symmetry. It's called individual symmetry or individual variation. Depend on what you want to call it, okay? So I'm just trying to use those languages so you can understand what I'm talking about. Individual variation or individual symmetry. So that is called symmetry. This one is symmetric now because it's significant. Now the two line here I color red. They are the most important line you need here under this symmetry. You know, in some other subject you don't need F, but here you need F, you need P because they are saying something. Both of them are saying something. They are important. All right. So you can see this F here now is almost 3 times of this. You see that? So it says something as well, saying something. So this particular side this is what you call sides. You have them for both object and for both matching symmetry. But in most times in matching symmetry they use size most times instead of reflection. So you can see instead of a side, you can say reflection here. Sometimes you see reflection, they say reflection, and that reflection means directional symmetry actually. That's what it means. You can call it side, all right? You can call it side, you can call it reflection, you can call it DA, directional asymmetry, okay? And this one, the first one, you can call it individual symmetry or individual variation. And this particular one is called FA. They call it FA. It's called individual by size or individual by reflection, all right, or simply call it FA. So when you see FA, sometimes you think, what are they saying? FA, what the meaning of FA? Okay, so what FA means that it means that individuals, this individual now multiply by this individual by this. When you observe this together with this, it gives you FA. So that is what fluctuating asymmetry. Okay, that's fluctuating asymmetry. So you have what they call HEMI, measurement error. This will always come along with it automatically. You have to present it along to know how, because that's why you have to repeat or a replicate of your digitization. So what is important here is SS, this one, sum of square and the mean square error, 0.01. So some people use this, some people use this, understand? So depending on the one you want to use from the two, all right? So this is what you get as a result. Now depend on what you are doing, depend on how you have to present it. Understand? People depend in different form, in different ways. So this is just a concept of the analysis. So I will quickly show us how to get this particular one, this one in Morphometrics, just in just few minutes now before I close up this particular section. We already have our We already have our data digitized. Don't forget that. So let me go Morpho-J now. Morpho-J. This Morpho-J. Morpho-J has a challenge when it comes to symmetry, actually. Okay. So I will explain that as we proceed, because we are not using the Morpho-J in this under this session, because for you to use Morpho-J, you have to still write a program in R for reflection for sides for reflection. You understand? You need to write a program in R for reflection, for you to compute reflection or side, so that you need to present your result accurately. Else, Morpho-J cannot do that for you automatically. Okay, so that's the challenge you have with Morpho-J. It can do symmetry for you, give you the shape analysis and the rest, but it cannot give you the result without computing the result in a R. But it doesn't have it inbuilt. So right, so let's see. If you come here now, you create a new data set now. For example, I want to browse our now. Before you go further, just select object symmetry. For example, just object symmetry. Say yes. So we want to look at it. Let's browse our TPS file. Okay. Where it is now? The class, any class. Okay. So we have phase 1. Let's just use phase 1 to TPS. That's our data set. So don't forget, I select this. I choose this 2-dimensional. Don't forget that. So let's browse this and see. So it has come here. So let's see here. This is our data set. All right. So we want to compute Roscoe now. This is this is called GPA now. Here, click here. You see now what to get. It gives you, because you are selecting object symmetry now. It gives you this automatically. Which means this your landmarking is accurate to compute symmetry. If it's not accurate to compute symmetry, it will give you error automatically. You will see that it will not align. This will not come out. Understand? It won't show like this to give you different thing. You will know that, oh, this is not correct. But now it's correct now, because it's giving you the paired and unpaired landmarks. So you can see the side here, the side there. So you can export this out, or just print screen it and save it, so that you can be able to follow it. In case you have many landmarks, sometimes you can have up to maybe 30 landmarks and the rest of them. So you want to pair, and you may be confusing. Sometimes you may not be able to which one that goes along with this one. Yeah, you might be confusing. So when that happens, just come here and run Morpho-J and look at the analysis. You'll be able to see, okay, if you are correct, then to give you this. But if you are not accurate, if not properly aligned or homologous, it will show you something else totally different from this. But it will not compute. It's not compute. That is the truth. It's not compute here. It won't come to this place to show you error, which means that the object symmetry is not accurate. All right. So let's close this, and next time we continue next time and see how to run it in how to compute it step by step. So that is that for today. I want to thank you for joining this class. I will see you in the next session. Thank you.